All right, now we're going. All right, so we're given voltage, we have resistance, we're looking for current. What's our formula? V divided by R, V divided by R. So 110 divided by 2200 equals what?
0.05.
0.05. So, or we could express that,
59.
oh, that's a big decimal. We could re-express that as 50 milliamps, whichever we choose. All right, how about the next problem on the left, bottom left? We have a voltage value of 12 volts and current value of 0.6 amps. What is our resistor and what's our formula?
Would be V over R.
Equals V divided by
So it'd be 12. Wow, this thing's seriously out of calculation, y'all forgive me for a minute. Trust me, it'll make this much easier for us all, especially. Okay, so 12 divided by 0.6 equals what? 20. So our resistor is 20 ohms. All right, let's look at the third problem. We are given a battery voltage of 18 volts. We're given a lamp that is 3 ohms. What's our formula and what's our current? 18 divided by 3. 18 volts divided by 3 amps, 3 ohms, I should say. Gives us what? 6 amps, right? Very good. You're all given a verbal 100 so far. Okay. Sneaking me in a little more. All right, we got 12 volts, we got 3 ohms. What's our current?
4.
4 amps. So we take 12 divided by 3. And again, we're referring back to this little Ohm's law pi. V equals I times R. We cover up whichever one we want. We want I, that gives us V divided by R. If you memorize that, you'll have all of this that you need. All right, a little harder here. We're given a voltage of 7 volts. We're given a current of 5 amps. What's our resistance? 7 divided by 5, 7 volts divided by 5 amps gives us what? 1.4 ohms. All right. 2 amps across 13, flowing through 13 ohms gives us a voltage of what? Yeah, that's simply I times R. So we can fill in the 26 in front of the volts there. All right, we have a current of half an amp, 0.5. I stole that one from the web, so don't blame me for not having a 0 there. We have 12 ohms, so what's our voltage? 6 volts. Everybody's caught up on that 0.5, having to multiply it. It is 6 volts. We simply take I times R, so 0.5 times 12 would give us 6 volts. All right, we're given a current of 10 milliamps, a resistance of 5K. What is our voltage?
50 volts.
50 volts. We multiply 5 times 10. Now, milli means 10 to the negative third. K means 10 to the positive third. So we can, in fact, just cancel those two out. We have the remaining math, and we have our 50 volts. All right, have a 12 volt battery, 2 ohms of resistance. What is our current? 6 amps. 12 divided by 2. All right. Very good. Here we go. We we have 5 volts, 10 mega ohms. Excuse me. What is I equal to?
Point five micron.
Point zero,
0 point, how many zeros? And then 5? So our formula is what? Let's see if we're right. V, I times R, right? We're looking for I, so that's gonna be V, which is 5, divided by 10 mega. That means 10 million. So it would be 5 divided by 10, 6 zeros behind. So we gotta make sure. We can also know it's gonna be expressed in microamps too.
Point five micron.
We can say 0.5 microamps, or even if we wanted to go milli, micro, and nano, that would be 500 nanoamps. But what would it be in decimal form? 3, 4, 5, 6, and then a 5. And I'm gonna write a couple of tailing zeros here. So what we did was we got decimal form. If we move it 1, 2, 3, that's milliamps. We go 4, 5, 6, that's microamps, which we got right there, 0.5. Or if we go 7, 8, 9, that gives us 500 nanoamps. So we can take that decimal, convert it to milli, micro, or nano. And of course, if we do correct engineering notation, that's what we would choose, because we say engineering notation has to be 1 to 999. But in practical standpoint, all 3 of those answers would be okay. All right, we have 10 volts, 5 ohms. We're looking for I. 2 amps. All right, we're gonna go to the fourth slide. We're gonna introduce you to a new formula we've probably already talked about. But in case we haven't, P is power. Power is how we typically measure the value of a light bulb, which is in what? Watts. So power is measured in watts. W-A-T-T-S. The symbol for power is a capital W. Now I'm going to show you an easy power formula, and then I'm going to show you a way, you can go online and get these formulas, but I'll show you a way you can calculate those formulas and get them. If you can remember pi, power equals I times E, or V, as we know they're interchangeable. So P equals I times E, or I times V. But what happens if we only know I and R, or V and R? How do we get a formula? Well, it gets a little fun, and this isn't really something you're going to be tested on, but I'll show you anyway. Let's say we have I and R instead of I and V. So we have P equals I, and we have R, not V. What is R equal to?
V over I.
We could say I times V. Actually, that doesn't work. Well, let's just say R is V over I.
If we're trying to solve for V, would it times
Oh,
I
excuse
times
me,
R.
that's why it didn't work, thank you. I knew for some reason that wasn't G-Hon, right? That's why you don't do math before 9 o'clock. Equals I times, and we're looking for the formula for V, which is I times R, right? There we go, that works much better. So if we solve that down, P equals I squared times R.
You can go wheel it out the door.
So we can actually make a formula by going back to our Ohm's law. So what if we have P equals, we don't have I, but we have V and R, well, we know, excuse me, that's what we just did, no, we have V and R. So we can say, actually, that's what we just did, hang on. So we,
So you got the resistance and the voltage.
so we have resistance and voltage. So voltage is actually a part already, and we're gonna substitute the I formula, which is V over R, right? So the formula for I is V over R, so P is also equal to V squared divided by R. So you can actually take and substitute what you're missing from its value in Ohm's law. Or, I'll give you another hint, if you wanna go Google and get the formula. But if you're ever out in the field and you only have those two and you're trying to figure it out, if you can remember P equals I times E, which is V, and you got the Ohm's law formula pretty well down, you can just do a substitution. So let's go back, we're gonna do all I times E though. We make, let's write down a couple, somebody write down the P equals V squared over R, and P equals I squared times R, and we'll try it and see if it works. P equals I squared times R, P equals V squared divided by R. Alright, we'll get back, see if we can actually make that work. Alright, let's first start with I times E. What is power for this formula? The 0.05, which is our current, that's our I, and our volts is 110. So what does that equal? How much? 5.5. Okay. 5.5 watts. Well, let's try one of them. We won't try both. Let's try I squared divided by R. So somebody take 0.05 times 0.05 and divide it by 2200. Tell me what to do. I squared.
No, it's times 2200.
Ah! So let's try that again. 0.05 squared times 2200. That math will work a little better. 5.5. So we find out those same formulas work. We'll try the other one. All right. So let's do the I times E here. 0.6 times 12. 7.2 watts. Let me tell you something in case you go home and try this. Some of you are going to go measure the resistance of a light bulb, a 60-watt bulb, and you're going to go, I want to be able to take that resistance and take the voltage, which is 120 volts, and be able to calculate out 60 watts. You won't, and that's because once that filament heats up, the resistance changes drastically in there. So the resistance you're reading with that bulb nice and cold is not what it's gonna read once it's fired and turned on and glowing. So,
Heat increases resistance, doesn't it?
I think it actually lowers it on the bulb. We can try that and see. We'll do a hot bulb, cold bulb
Yeah, it's been a while since I played.
sometime. I think we did it with that little 12-volt lamp down there, and I think we found that you had to heat it up. If you heated it up, turned it off quick and measured, I think it actually lowered a little bit. But you gotta remember that's in a vacuum, so some properties
Yeah,
may change. All right, I times E here.
108.
6 times 18,
108.
108 watts. So that actually gets into the, about what a 100-watt light bulb would be. It'd be about 3 ohms, well, if it were 18 volts. So if you've got a 50-watt bulb across 12 volts, that tells you a little bit about what kind of load you would be seeing. All right, what was the other one? We did the I squared times R up here. What was the other one? All right, so let's do 12 squared over what, R? Over 20 for this one, and let's see if that formula also works. So it'd be 144 divided by 20. 7.2 watts. So we found out, even though we kind of created those formulas from scratch, they're legitimate formulas. We went through the process. We see that it works. We'll continue with I and E henceforth, just for time period. All right, what is I times E on this one here?
48.
48. 48 watts. All right, how about here? I times E, 7 volts, 5 amps, 35 watts. How about here? I times E, 2 watts. I times E here, 3, 6 volts times 0.5 amps, 3 watts. Here, 500, what? 500 blank watts. Micro?
Oh, that's the.
Nope.
No.
So it's 50 times 10 milliamps. So it's 50 volts times 10 milliamps. So what's our answer going to be in?
Should be 500 milliwatts.
500 milliwatts. There we go. Because we don't offset, if that were 50 kvolts times 10 milliamps, we'd offset. But it's straight 50 volt units, we got 10 millis. And we could express this as literally 50 times 0.010, because that's 10 millis in decimal form, and we would come out with 0.5 or 500 milliwatts. All right, how about here? 12 volts, 6 amps, 72 watts. All right. How about here? I times E. It's still interesting. What's 5 times 500? 2,500. And that's going to be nano watts. Now we can convert that to 2.5 if we move that decimal from here, 1, 2, 3. What does that change it to? Microwatts. And that's in true. So a very small amount of current. And that's what you'll see is that's why today's electronics are not eating up our battery life. They're literally down in the, in some cases, microwattage, right? All right, how about the last one? I times E. 20 watts. And again, we should be able to take any of those formulas and apply to these, the I squared R, the V squared over R, and we should be able to get wattage the same way. It's just much simpler if we take I times E. Questions on ohms, law, wattage, and so forth? All right, let me get you to do something here for me. We are about to do a lab, and this lab is in your text. But all it is it's asking for an answer. Don't try to type an answer because your instructor is going to have that. After you complete the lab, we'll type in the answer, and you'll get 100 if you type in the right answer. If you don't, we'll get complaints. it hadn't changed the rest of the I know. I heard. It's coming. Just hang on. But keep in mind,
While we're speaking of grades, the pre-assessment grades count?
so here's what I need to do. Take out a piece of paper. Alright, so each of you in here, write A, B, C, D, E, F on a blank piece of paper. And then at the bottom, write that question. And once you have the right answers, I'll sign that paper. Mr. Lee is gonna be coming back to each of your computer. You need to go to the DC measurement test in your computer. And there is a fill in the blank question that he will write something in that is the correct answer that will give you once he sees your signed paper.
You realize that makes no sense.
This just keeps us from having to get y'all to turn in a bunch of papers and us grade them and waiting, whereas we can just type in the correct passphrase, you get the automatic 100, and you can take your paper with you, and I don't have a bunch of paper on my desk. So, it may not make sense from your perspective, but from mine, it makes a lot of sense. So, no, you'll be bringing a piece of paper with you. So I need both of these Amprode meters and the Klein meters, and I'll bring the Klein up here in just a moment. They start out in AC, and that's because they're electrician meters. And 9 times out of 10, as an electrician, you'll be measuring AC above DC. So we have to change them from AC to DC. And I'm in the volt selection. I'll slide that up just a little bit so you can see. And you'll see right here, I've got a wavy line in white and the dotted and dashed line in yellow on this Amprode. To change this AC to DC, DC is illustrated in yellow, so any function in yellow, I'm going to have to press the select button on this Amprode. And if you'll notice, the AC up here, well, actually I have a point right here, will change to DC when I do press the yellow button. So you can see in the upper left now, I do have DC. So it's a multifunction meter, and rather than have some of the flukes, which I like better, just because I was teased on a fluke, we'll have a separate DC and AC setting for voltage. But these Kleins, these Amprodes, which are probably pretty good meters in their own right, and probably about half the price of what their fluke alternates are, typically have this selection button where you have to press between the different ones here. So obviously, and here's the funny thing, the microamps, the milliamps, and the amps default to DC, and you have to press select to do the AC on there. So it's going to vary a little bit meter by meter, and I want you to see these different meters because unless you have your own meter, and some companies will not let you use your own equipment. Some will, some won't. It all depends on the company. They're worried about the liability standpoint of one, replacing your equipment if something goes bad, and two, if it's faulty, that, the liability from their standpoint. So it all depends on where you go as to whether you'll use their equipment, your equipment, or whatever the case might be. But if we take a look on this one, we see virtually the same thing. Volts is expressed with the wavy line for AC as white, the orange or red as some of you call it. I'm not sure which of us is colorblind, but I call that orange. The straight line is in orange, so to change that wavy line, which represents AC, I'm gonna have to press the orange button, and it'll change to DC. So again, getting our meters to a particular setting can be a little challenging. I've got a Fluke in my office. Paul, if you wouldn't mind grabbing that one, you'll see a Fluke meter with a yellow case. I'll show you the difference. The display on it is just about faded out. It's probably 20 years old. It's been dropped off rooftops and it's held up, but the display is getting pretty doggone dim on it. But I'll show you that one just as a point of reference to give you the differences in the meters and things you have out there. And they all have different ranges of functionality. The Flukes typically don't do the fancy stuff like reading capacitors and stuff like that.
Mr. Radley,
Yes.
you can't use one of these in place of one of them, can you?
I mean, they'll do some of the same things. So, yeah, I mean, absolutely. You
They
can,
don't do
depending on
really.
what you're trying to do. And you see this poor guy has been through the mill, literally. But it really is probably 25, 30 years old. And you'll see how faded the display is here in a second. But obviously got a separate voltage AC and voltage DC on this one. So it's just a matter of choosing on this meter by a selector knob. So some of them have the multi-function button, some of them have a selector knob, all just depends. So let's go back to either our Klein or our Ampro, which is what most of you use. And they're very similar. There. So I'm measuring DC voltage. Now the first thing we did was we measured our little coin battery, or at least the first one in the list. Might have jumped around a little bit. And a coin battery, one side is positive, it's typically the larger side that comes on up, and the other side is negative. And you'll see, if I can get it up on the screen, you'll see a little plastic separator that separates the two sides. So if I want to read this battery, the least awkward way to do it, let's see if we can still see the display. The bigger side is my positive, the smaller is my negative, and you see I'm reading 3.2 volts. Can y'all see that on the screen?
Yeah.
I can't turn around,
Yeah.
or I'll let go of the leads. Now another way to measure that, if you're not quite able to do that on a tabletop, or if you don't have a tabletop nearby, is just simply hold it. There's not your body is typically low enough resistance-wise, especially to a little battery like this, you're not going to conduct enough to take away from the reading. So here's a battery this size, about the size of a nickel. It's reading 3.2 volts. The next thing I gave you was a AA battery. Let's read it, and we know the tip typically is positive. So these are a little more awkward to read, and this is how you can really stick a lead in your hand if you're not careful. So we're reading 1.5 volts. So some of you may be asking, how can this itty bitty thing supply 3.2 volts? And this much bigger battery supply 1.5 volts. What's the difference between these two batteries besides voltage?
Material,
Material. But what ultimately?
One's the alcohol.
the use.
The use. What does use come down to? Am I going to have a flashlight that has this type of battery in it right here?
No.
No. It's going to be some low current application. And that's the key. This is used, typically you'll see this in a PC as a battery that retains BIOS settings. And it uses very, very low current. Remember when we talked about capacity of a battery? This has a very low capacity. This doesn't have a huge capacity, but it has a lot more current capacity than this little coin battery does. So if I had a flashlight that ran off 6 volts and I put 4 of these together to get 6 volts, I could probably power that flashlight for a few hours before it died. If I stuck 2 of these together and somehow wired that same flashlight to run off these, it'd probably be measured in minutes. Because it's not going to last a long time. Even an LED one would not last hours like it would with a couple of these. 2 of these would make 4 of these would make 6 volts. 2 of these would make approximately 6 volts. But the difference is going to be the capacity, how long they're able to power something. Might not even turn the flashlight on. Might not even be enough power, meaning current and voltage combined, to even turn that flashlight on. It just depends on the battery. Depends on the source, I should say. So I had 1.5 and 1.5. And I threw you a semi-dead AAA battery in the mix that some of you had. Some of you had a C battery here. But all of these are 1.5 volt batteries. This one's getting a little on the dead side. So it's already been utilized and we've just about killed that battery. But here is a C battery, and it was actually your C if you were on the first part of this experiment. I added a few more batteries to kind of speed us up. We're about 1.5. We're a little shy. We've used a little bit. But again, the difference in these three, they're all 1.5 volt batteries, but they're going to have different amp hour ratings. This one's going to be smaller. This one's going to be a little more. This one will be a little more. So if I were to take that same LED flashlight and run it off of a couple or three of these versus three of these versus three of these are going to last longer. These will last a little less long, and this will be the shortest of all. It's just capacity there. I actually had a little tripod light one time that was LED, and it operated off of 3 volts. And it used 2 AA's, but it had 3 legs. I could put 2 AA's in leg A, 2 AA's in leg B, and 2 AA's in leg C. And what was happening was each one of those legs was in parallel with one another. So that just upped my capacity. It would run off one leg's worth of batteries, but if I went ahead and loaded the other 2, it just helped my capacity last a little bit. So then I threw this guy, which we all call a 9 volt battery, but I covered it up. But when we actually measure it, we'll measure 9 volts, or approximately 9 volts, 8.9. This one's had a little bit of use. Typically, if it's brand new, we'll measure 9.1, 9.2 a lot of times. And if we're ever concerned or want to know what the positive terminal is and the negative, all we got to do is put our leads on it. If we can't remember, it's actually marked on the battery. But for some reason we can't remember, we get 8.91, but notice I got a little negative sign to the left of the 0. So that means I've got my black to the positive and my red to the negative. Now you want to throw a technician off and have a little fun with him?
Oh,
Yeah.
Swap these 2 right here. Because then they're looking at the red lead going, this is my positive and this is my negative, but they're swapped on the meter. So don't do that. That's one of those little tricks, like I one time swapped the comma key and the period key on a keyboard. That'll mess some people up too, especially when you type in www, Amazon, com instead of .com. You can't really see it on the display. But you do want to make sure, if you're ever out there reading things that you think should be positive and you're getting a lot of negatives, you may have swapped these leads here, or some jokester may have swapped those leads on your behalf down here. These meters are typically designed that the black always stays in common. The only one you ever move is the red, and that depends on whether you're reading voltage or current. Some of you read a little DC power supply, which was the E, the one that was taped to the table. Again, everything has a positive reference point, but depending on where you put your black and your red back there as to whether you read a positive or negative. But if you need to know which one, if your kid's got a Barbie Jeep and it needs charging at 6 volts and you want to make sure you put the positive and negative, all you had to do is put your leads down. If you're reading a negative voltage and your leads are right in your meter, then swap your leads, and now you know which one's positive and which one's negative as soon as you get a positive reading. Some of you had the biggest trouble on the power supply back there, had it set to 15 volts. Those power supplies have a circular terminal on them. And what it is it's just a barrel, and the outside contacts of the barrel are copper. May even be gold tin, I'm not sure, it depends on the supply. What a lot of you were doing was you were sticking your lead in the hole, and that was it. You weren't touching anything. But when I told you to tilt them back a little bit, that lead would dig into that barrel. So that's why some of you had a little trouble hitting that supply back there, was we weren't really contacting the contacts. The holes are just that, holes. And what they're made for, if you can't really see it, you can on these. They're made for these little banana jacks, and they look a lot like a banana peel. I'll put them up here. See how they got kind of a little banana look to them. They're called banana jacks. They're made where they can plug in, and obviously all these little outer bands of this thing grip that terminal when they go in. So that's what they're made for. So if we want to hit those, we've got to, you know, our lead probe is much smaller than this banana jack. So we've got to tilt it up so as to dig in back there. So any questions on what you did, these meters, the different kinds of meters, measuring DC voltage and understanding what you just went through? Because you're going to be tested on it later, and I'd rather hear questions now than after the test. All right, so we got it down pat. So let's have a test. I'm just kidding. Let's take a quick 5-minute break, and then we're going to get back. All right, here we go. So let's do series circuits. All right. Most circuits are going to contain components in series and or parallel. Most everything you're going to deal with, at least down to a system type, is going to have series and parallel. This is a simple series circuit. All the components are in series. This is a 2 resistor parallel circuit. Those two are in parallel. And a series circuit is a circuit that contains only one current path. And if you look, we've got power coming in, goes through this resistor, this component, and back out. And you can see it right here. Even though it's not laid out in reality, as pretty as it is on that schematic, it is a series circuit. And that's why we make schematics, is it'd be awful hard to look at this board and see this. So if we have a schematic, we can a little more understand what's going on. And typically on your board, these would be labeled R1, R2, R3, so forth. And total series resistance is always the sum of the resistors. Again, we beat that horse to death. You got 4 resistors in series, R1 plus R2 plus R3 plus R4. Talked about this already. The current is the same at any point of the circuit as what's at the same point of any other part of the circuit. So it doesn't matter if I measure current here, 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 or here. Theoretically, I'm going to measure the same current. There are some very, very minute line losses due to wire resistance, but for all intents and purposes, it is the same current. Voltage. If we have more than one resistor, i.e. more than one load, then the sum of the drops is going to equal the applied voltage. These are rules that always apply to series circuits. We add up the voltage drops, they're all equal to source voltage. We open that circuit anywhere and put an ammeter in there, we're going to measure the same current no matter where. Power is the same way. If we calculate the power through a resistor, it's going to be the total power of circuit. So if we take the applied voltage times the applied or the actual current, we're going to get power. Then if we take and multiply the voltage drop times the current going through resistor 1, the voltage drop times the current through resistor 2, the voltage drop times the resistor current through resistor 3, and add up all those power factors, it's going to equal the total power factor. And again, here it is. The total resistance is equal to the sum of the individual resistances. R1 plus R2 plus R3 would equal R total for this circuit right here. The current at any point in the circuit equals the current at all other points, or any other point. Not all other points, but it really is any point. So if I break it here, if I break it here, if I break it here, or if I break it here, I'm going to have the same current no matter what. I'm going to have a voltage drop here. I'm going to have have a voltage drop here, I'm gonna have a voltage drop here. These three voltage drops should add up to my applied source voltage. Again, another rule that applies to series. So if that voltage source is 12 volts, and those resistors are all the same value, what is each resistor gonna drop? 4. And that just happens to be because they're equal values. If I'm applying 15 volts, and those three are all the same value, what am I going to be dropping at each one? 5, yeah. So if they happen to be equal, I can calculate the voltage drop. If not, I'm going to have to add up the resistances, get my total resistance, divide that into my voltage, get the current, and then take that current and multiply it by each resistor value to get the voltage drop for that particular resistor. And again, we talked about the power. We can calculate power that this resistor is drawing, the power that this one is, and the power, and when we add all them up, that's the total power of the circuit. All right, this is what everybody in electronics loves, and this will be one of the few times you'll hear me say Kirchhoff. Kirchhoff has this voltage law, and it gets into loop equations and everything else. Unless you're in design, you won't use Kirchhoff. So guess what we're not talking about? Next slide.
Thank you.
Kirchhoff basically says, hey, if we add up all the voltages, they equal the sum of the applied source. But then we get into some nice algebraic loop equations. If you're disappointed, I'll find you some extra work. I promise. And again, it's just showing if we apply 10, this one drops 8, this one has to drop 2, and 8 plus 2 equals 10. And the way he says it is, we'll make some of them positive and we'll make some of them negative, and they'll have to add up to 0. Yep. And all he's saying is if our source is positive and these guys are negative, positive 10 plus negative 8 plus negative 2, or negative 10 plus positive 8 plus positive 2 equals 0. So again, it's just a different way of saying the sum of our drops across the resistors is going to equal source voltage. But this guy got his name in books, and we have to teach it, and I absolutely hate it. Enough said.
It was his doctoral thesis in the 1800s.
So, as far as anything to do with Kirchhoff's, and I need to tell Mr. Lee that, so I'm going to pause that to let him know that he doesn't have to go through Kirchhoff's. So we're not doing Kirchhoff. Anyway, now this is where you need to really be paying attention. Don't worry about this Kirchhoff stuff. This is the part that throws everybody when it comes to troubleshooting. We've got this circuit. It's got a 1K resistor, and it's got R2. R2 is open. Now these little ground symbols are basically indicating that these are at the same points. So we can redraw that circuit to look just like that, but we can also understand what those ground symbols are. And all that means is we're taking this back to the negative lead of the supply. This is indicating the negative lead of the supply, so we can redraw that circuit that way. So R2 has opened, okay? So we would normally have a circuit path, whether you start negative, positive, or positive, negative, doesn't matter, of current flowing through R1 and then coming through R2, but it gets right there and there's no path for it. And it can't get back to the negative side, or again, if we started on the negative, we're going to get here and stop. So again, I done told you current's up to you. I don't care which way you go. So we've got an open circuit. It's just like flipping a switch open. What will we read across R2?
12 volts.
12 volts. Everybody's mind, mine included at times, wants to go, oh, if it's open, you'll read nothing. But you're going to read applied voltage without any drops. The reason for that is to calculate a voltage drop across this resistor, we have to have current flowing through it. If current's not flowing, this guy's not dropping anything. And when we put our meter on, we put our negative lead here, it's going through this part of that broken resistor back to here. We put our positive lead here, it's going back through here, This guy's not got any current flowing through it. It's just taking us back to source, and we're gonna read source voltage. Our mind wants to make us think it would read 0, or this guy would drop something at the very least. But this guy's not dropping anything because there's not a current path. The only way we can have a drop is if we have a current path back to the source. So a resistor doesn't drop anything when it's set up, when we've got this set up right here. We'll read source voltage. And we'll actually try to bring down some proto board tomorrow or sometime soon and actually illustrate that for you. But that is a fact. All right, so circuit current drops to 0 and source voltage is dropped or read across that open component. That will always, always, always be true. Now let's look at this. What if we've got multiple opens? We've got to get back to the source. If we have R2 and R4, if we tried to read here, if I tried to read across R3 with a meter, how many volts? 0. Because I can't go this way and get back to my source, and I can't go that way and get back to my source, so I'm going to read 0 volts across R3. But if I go to either side of my open here, R2 takes me back here, R4 takes me back here, and I would read source voltage. But across R1, there's no current flow, no voltage drop. Across R5, there's no current flow, no voltage drop. So I'm going to read source voltage if I happen to read there. You're going to get played with some of this. Don't worry. So let's say shorted resistor happens. Now, these are opens, right? They're broken. That's an open. Remember our switch? That's open. This is closed. But when we talk about a resistor missing or a resistor being bypassed, that becomes a short. So if we've got a schematic that looks like this, this is 12 volts right here. This is a 1K, and this is a 1K. So what is each one of those dropping? 6 volts, right? Now, if something shorts one or the other, we could redraw this circuit. We'll say it shorts this guy up here. Okay, we'll make it the other guy since I forgot to. So here's our 1K, and here's our other one. But what has happened is a glob of solder or something has shorted around it. It's no longer part of the circuit. We could either put a straight piece of wire there, so when it was manufactured, instead of putting a resistor there, the person on the line, it may be Monday, they put a piece of wire there instead of a resistor. Or if we actually look on the board, here's the holes for the resistor, and when we go to solder it, so maybe when you were back there soldering it, we drop a blob across it. That's the same as putting a piece of wire there, even if the resistor's there. Because what we'd have would be this resistor here, but because we got that large blob of solder, we're shorting out that resistor and putting it right there. So what happens to R1, this one right here, how much is it dropping now? 12, and there's no drop here, right? Because we got a straight path. The voltage across the shorted component is 0. The voltage across the other components increase. So let's draw that again. Let's put 3 resistors in. Let's illustrate this point. So here's my PCB board. I'm actually going to draw a little hole that illustrates my resistor. I'm gonna draw another little hole here. I'm gonna draw a little hole here. Draw my resistor, another hole, come down, another hole, resistor, another hole. So let's just imagine we had a PCB board, and these are actually holes that our resistors go in. This is 12 volts. These are all 100 ohm resistors. Okay? So what am I dropping across each one of those when I'm working correctly? 4 volts, right? Because they're all the same value. Now, if they were different values, we'd have to do the calculation. And we'll do one like that in a minute. Well, let's say when I put this resistor in, you know how we kind of bend the leads toward each other? Let's say I forgot to trim those leads, and I soldered it in place. It's a bad day, it's Monday, I'm hungover, come in after St. Patty's Day or something. And I touch those two leads together. What have I effectively done if I touch those two leads together right here? I put a wire there, right? I had shorted that component. I hadn't opened it, I have shorted it. Even though that resistor is still intact, path of least resistance is what the current's going to take, and a wire certainly has less resistance than a resistor, just by the very nature. So now what's going to happen to these 4 volts drops? This one will go to 6. This one will go to 6. What about right here? 0. So what can happen in the field, especially if you were working on component level board, is the resistors may visually be there, and you go, well, no, R1, R2, and R3 are there, and then you turn it over and go, I get it. There's a short on the back. So that's what effectively happens, is we read no volts across here, but these voltage, which would normally be 4, are suddenly shot up to 6. And the same thing can happen, you know, I've been using equal resistors because I'm lazy, and it just made life a little easier. Let's go back and use unequal values. So we'll say this is 100, this is 200, and this is 300. This is where it gets a little interesting too. We'll start troubleshooting these circuits. What's my total resistance?
600.
What is total current? 12 divided by what? Which is what? 50 milliamps? 0.05?
Yeah.
50 millis? Is that right? Okay. I'm mathing in my head, so it's 600, let's make sure, 12 divided by 6. I did, it's what? That's why I get some mathing in my head. Y'all want me to correct?
0.02.
Yeah.
Y'all work, live for correcting me. What is it?
0.02.
102 or 20 billions.
I'm thinking 12 times
All right,
50.
so there we go. Now we're right. So through this guy, we got 20 billions. But here's the reality of what really happens when we short a resistor. Which one do you want to short? 100, 200, or 300? 300? All right. We're going to short that guy out. We came in with that St. Patty's Day celebration. You soldered them two leads together. You're having a bad day. Now what really happens is this. What is my total resistance now? 300 ohms. What is my total current now? How much? 0.04 or 40 milliamps. There's a couple of things that can happen. If these things weren't rated to handle 40 milliamps, we may let the smoke out of these guys. They could burn up. But if not, if they hold, we're going to get some some more inaccurate readings, what we're gonna get is, we're gonna see, instead of, the even voltage drops, well, a while ago, we wouldn't have seen even either, but we can go back to that, but, so what is 0.04 times 100, what are we dropping there? 0.04, 4 volts, right? What are we dropping here? 8. What are we dropping here? Nothing. So before she replaced that part and had a bad Monday, I'm picking on you because you're the one that chose short. Before whoever replaced that part and had a bad Monday, we had 20 milliamps, right? What was the voltage drop across with the circuit working? What was the voltage drop across this guy?
2,
2 volts. So R1 was 2 volts.
4,
What about this guy?
4, and 6.
R3 equals 6. So they applied, which was 12, equals the sum of the drops. But we saw 2 things happen. Current changed as a result of that thing being shorted, and our drops changed, because we should be seeing 2 here, 4 here, and 8 here, and we started seeing 4 here, 8 here, 2 here, 4 here, and 6 here, and we saw 4 here, 8 here, and nothing here. So that would be indicative that something's going on that shouldn't be going on. Now our sum, 4 plus 8, still equals 12, but we're not dropping anything here. So if that globs on the back side of that board, we've got to turn it over and investigate. See what happens. So that's what can happen when we short a resistor, and it does happen. And it can happen either through those leads not being trimmed. We used to have solder splatters that would, the way these circuit boards are built at Rockville and most every other plant, is there's not a person out there with soldering iron, hand soldering all those joints. There's a machine that has a rolling wave of hot solder that this thing glides over. And the solder tends to just stick to the metal and run away from the fiberglass. And what comes out with are these nice, pretty even joints that looks like the best solderer in the world did it. But every once in a while, that solder station, that wave solder machine would burp, and it would splatter solder up on the board, and it would do just what you saw there. And the other thing that can happen is that operator, we had some boards we built back here that we mixed the resistors up. They may be mixed in the cabinet. I may reach into the 1K resistor cabinet and a 1 ohm resistor being there, and that's almost a dead short. So we can see the same characteristics just by applying a wrong resistor in there. 1 ohm is not far from short. It would be such a little drop we would barely see it. It would bring it down to probably like 3.98 volts and 7.96 volts, and then just a very teeny weeny little drop here, depending on what those values can be. So when we troubleshoot, we've got to get a little understanding of what's going on and how these things, cause and effect. But by knowing these rules, we can know that a little more.
How did you bring it?
I don't know, that's weird. There it went. Just disappeared. So there's this nice formula that they're trying to show you that voltage across the short component 0, the voltage across the other. So basically, to get total source voltage, we have to take the voltage drops across the remaining resistors that aren't shorted and add them together, because the shorted one, by its very nature, is just not going to have a drop. Probably won't get into voltage dividers much, but what they basically do is, by being able to tap into a resistance, we're able to divide voltages up, and that gets into really parallel circuits. I'm not even sure why they threw this into series circuits, so we'll skip that for right now. All right, let's talk about this right here. Ideal voltage source maintains a constant output regardless of the resistance of its load. Versus a real voltage, the internal resistance causes a decrease in load resistance, which results in a decrease in the source voltage. All that simply means is, if we have an ideal voltage source, when we plug a load into it, we won't see a drop but in reality, most things are not ideal. You take that 9-volt battery back there that's brand new, and this guy mentioned it in this measuring video yesterday when he was measuring batteries. We measure 9.1, 9.2, we may measure 1.6 on a 1.5 volt cell. That's because it's not under load. When we put it under load, it drops down to more like the 9-volt range for a 9-volt battery, 1.5 volt range for a 1.5 volt battery. And that's just because there is some drops associated with applying a load. And again, we're getting into parallel. I'm skipping that. And this is far beyond what we do today. So that's pretty well it. So what questions do you have on series? Anything at all? Let's test.
Yeah, better
Yay or
get it out
nay?
before you forget.
Yes.
I got it. If you want to test, raise your hand. All right, looks like the no's have it. So we'll test tomorrow, but there's more to come. We're going to get in parallel tomorrow. Drinking coffee, wear your thinking hats tomorrow. We'll test first thing in the morning. We'll see then.
Parallel is not that difficult. Series is not that difficult. The series circuit, your current stays the same. Voltage drops. Parallel, your voltage stays the same, but your current drops. When they go together, parallel and series, then you
All right.
makes my head explode.
Yeah, I'll take it over here. That's right. I've got a help desk ticket on that one, so they will eventually get to it.
Oh, yeah,
It'll be all right.